Hello students, welcome to EPG Pathshala Biophysics. I am Dr. Ravi Majumdar, Emeritus Professor, Department of Natural Sciences, West Bengal University of Technology in Kolkata. Formerly I was Professor and Head, Biophysics Division, Shaha Institute of Nuclear Physics in Kolkata. Today we will be talking about Schrodinger equations in modern quantum mechanics. As you know, the name of the paper is Quantum Biophysics. Now, in the previous lecture, we have learned about the wave-particle duality of the electrons. Well, we have seen that the electron shows a diffraction pattern, and also we know how to calculate the wavelength or the de Broglie wavelength of electrons moving with a certain energy. So once we have identified the motion of the electron with a wave motion, then we must solve a wave equation to find out the energy levels of the electrons. So on the basis of wave-particle duality, one can obtain a Schrodinger wave equation. Well, I must remind you that actually there is no formal proof of Schrodinger equation, but on the basis of wave-particle duality, we can make it plausible. And once Schrodinger equation is obtained, then we have to solve Schrodinger equation for various systems, and that will automatically give you the discrete energy levels of the system. And in addition to the discrete energy levels, it will also give a set of wave functions which are very important in modern science. Because if you know what are the wave functions of two participating atoms in a molecule, then you can construct the molecular wave functions and then study the electronic structure of a molecule. So with this introduction, let me summarize the objectives. The objectives are the following. One, with the wave nature of tiny electrons leads to Schrodinger equations. Now the Schrodinger equations has both time-dependent and time-independent forms. Time-independent form of this equation is useful for isolated atoms where an electron is subjected to Coulomb potentials that do not change with time. And number two, the Schrodinger equations are expressed in operator forms which look quite the same in 1 and 3 dimensions. Like numbers, the operators may not always commute. Significance of commutation relations for operators is discussed. Finally, the time-independent Schrodinger equation in 3 dimensions is expressed in spherical coordinates for future use in the case of electrons in atoms, where an electron is subjected to Coulomb potentials that are constant on the surface of a sphere. Let me show you the picture of Erwin Schrodinger, because the entire lecture is on Schrodinger equation. And Schrodinger equation forms a landmark in modern quantum theory. So it is actually a wave equation, a differential equation, and it has got the same importance as Newton's equation in classical mechanics. But to solve Schrodinger equation, of course, is not so easy. Before that, let me tell you about the time-dependent Schrodinger equation. Now, as I said, it's not possible to derive Schrodinger equation, and we can only make it plausible by assuming the wave nature of matter. And then, is it feasible to describe the motion of electron by a single wave? Now, in view of uncertainty principle, delta x, delta p of the order of h cross, there is an inherent uncertainty delta x in localizing an electron in space, and this always causes an uncertainty in its momentum delta p, as I told you in the last lecture also. Since the de Broglie wavelength lambda is equal to h by p, this uncertainty delta p clearly implies a spread delta lambda in the electron's wavelength. So in real life, the motion of an electron is best described by a wave bracket, which represents a superimposed group of waves having wavelengths between lambda and lambda plus delta lambda, where delta lambda is the spread in the wavelength, and the particle velocity actually coincides with the group velocity. But here, for the sake of simplicity, we will describe an electron of momentum p by a single wave having lambda equal to h by p only. We are not representing it by a group of waves, we are simply representing an electron motion by a single wave. It will be shown that less general single wave description is fair enough to make the Schrodinger equation plausible. So if a particle like electron moving along the x-axis is represented by a single wave similar to wave propagation in a pond, the displacement of the wave at any point x and at any instant of time t is given by capital psi as a function of xt equal to a cosine kx minus omega t, as you can see on the screen, or this can be written as psi xt equal to a cosine 2 pi small t by capital T minus x by lambda. Well, this is because the wave number k is equal to 2 pi by lambda. K is the wave number, and this is equal to 2 pi by lambda, where lambda is the wavelength, and the angular frequency omega is 2 pi nu, where nu is the frequency, which is equal to 1 by t. So omega can be replaced by 2 pi by t, where, as I said, lambda is the wavelength of the propagating wave, nu is the frequency at which the crest and trough occur, and t equal to 1 by nu is the corresponding time period. Now, if psi is a complex function, we may generalize the equation to psi xt equal to a e to the power I kx minus omega t. When we are discussing bound state problems, psi is real, but in general psi can be a complex function. So for the sake of generality, we are expressing psi as an exponential function as shown in the screen. So the cosine form is just the real part of this equation. So using wave particle duality, E equal to h nu equal to h cross omega and p equal to h by lambda equal to hk, to translate the wave parameters into the particle parameters, we get psi equal to a e to the power I by h cross px minus et. So here we have replaced the wave parameters by the particle parameters, which are the momentum and the energy. So this is the first equation which you can see on the screen. In order to obtain the general time dependent Schrodinger equation, we can differentiate this partially with respect to t and rearrange the term. So we get E psi equal to IH d psi dt, and then differentiating the same equation partially twice with respect to x and rearranging terms, we get p square psi equal to minus h cross square partial differentiation del square psi by del x square. So you can check these by actually differentiating the first equation on the screen. Now, if you use the energy momentum relation, E equal to p square by 2m plus v, and if you multiply both sides of this equation by psi, then you get E psi equal to p square by 2m psi plus v psi as shown on the screen. So if you combine this with the previous two equations for E and p square, then you get IH d psi dt equal to minus h cross square by 2m d square psi dx square plus v psi, where h cross is of course h by 2 pi. So this is the time dependent Schrodinger equation, where psi xt is the wave function. This is a time dependent wave function. The potential is a time dependent potential. So you can see the time dependent Schrodinger equation, where the potential is a function of x and t, and so is the wave function. Okay, but you see, when we are considering electrons in an isolated atom or molecule, then it experiences a potential which is time independent. For example, the Coulomb potential is time independent. Well, it is simply Ze square by r in the case of a hydrogen atom, for example, where it only depends on r, that is the space coordinates, and not on time. The time-dependent Schrodinger equation comes in only when you place the atom in electromagnetic radiation, for example, where the light contains light. The presence of light is a time-dependent perturbation. So only in that case we have to talk about time-dependent Schrodinger equation. So let us now pass on to the time-independent Schrodinger equation, which is less general than the time-dependent Schrodinger equation, but that is the equation which the electron obeys when it is a part of a bound system like an atom or a molecule. Yeah, before we come to the time-independent Schrodinger equation, let me just tell you a few things which are important. In quantum mechanics, the momentum operator is defined as P with a hat. Well, that signifies that it's an operator, which is equal to h cross by I ddx, or minus IH cross ddx. Well, this is an operator. Differentiation, partial differentiation, is really an operation. So the Hamiltonian operator, or the total energy operator as it is called, becomes p square by 2m plus v, that is equal to h. H equal to p square by 2m plus v equal to minus h cross square by 2m d square dx square plus v. And if you introduce this, then the time-dependent Schrodinger equation can be expressed in the operator form, which looks very simple. IH d psi dt equal to h hat, that's the Hamiltonian operator, times psi. So it is important to note that in quantum mechanics, you see some dynamical variables like momentum behaves like an operator, and h really is the energy operator, which is called the Hamiltonian operator. Well, now let us come back, that is the time-dependent Schrodinger equation. If the potential V doesn't depend on time, that is for bound state electrons in isolated atoms, we can separate out the time factor for the wave function psi. If we separate out the time factor, then it becomes psi xt equal to e to the power minus I by h cross et times psi x. So if you plug in this equation in the time-dependent Schrodinger equation, and if you rearrange the term, then you can check. You can take a piece of paper and pencil and check that you get the time-independent Schrodinger equation, which is d square psi dx square plus 2m by h cross square e minus v psi equal to 0. So this is the time-independent Schrodinger equation where the wave function psi is independent of time. And this applies to bound state like atoms, where electrons form standing wave patterns. Well, we have seen that the electron forms standing wave patterns in the last lecture, and you see, for your attention, I have included this particular figure again, which you can see on the screen, that the electron in an allowed orbit of an atom, it forms a stationary wave pattern or a standing wave pattern. So this is the same diagram which was shown in the last lecture. That is, this is the electron wave pattern for the state n equal to 3. That is the second excited state of a hydrogen atom. So you see, we can also describe the standing waves by, you see, putting time equal to 0 in our equation for psi xt, and we describe this wave function by small psi, which is equal to capital psi x, and the time is put equal to 0. So the dependence of time is taken out, and you get a cosine 2 pi x by lambda. So if you can realize this, then this will provide you a easier method of coming to Schrodinger equation. So what you do is you differentiate this equation twice. So you get the first equation on the top of the screen, and then use the de Broglie relation lambda equal to h pi and e equal to p square by 2m plus v. These are the two equations which you already know, the de Broglie relation and the energy momentum equation for the electron. If you do that, then you get lambda square equal to h square divided by 2m e minus v. So if you combine these equations and rearrange terms, then you get the time-independent Schrodinger equation. So this is a simpler way of arriving at the Schrodinger equation. And as I said, this is not really a proof, but we are just trying to make the thing plausible by assuming that the electron can be represented by a single wave. So we will most often handle time-independent equation only in my lectures. So now you can also write the operator form of the time-independent equation. So the time-independent Schrodinger equation can be sort of rearranged, and it can be written as minus h squared by 2m by dx squared plus v psi equal to e psi. The first equation on the screen, and you see the term within the bracket on the left is just the Hamiltonian operator, which we have introduced. So in the operator form, this equation looks very simple, which is h psi equal to e psi. So this is the time independent form of a Schrodinger equation expressed as an operator equation, where h is an operator. The solutions involved a discrete set of energy levels and wave functions known as the eigenvalues and the eigenfunctions. Eigenvalues means the allowed values of the energies, and eigenfunctions means the corresponding wave functions, because psi is called the wave function in quantum mechanics. So once the operators are introduced in quantum mechanics, it must be realized that these operators do not commute. So in the screen you can see commutation relations for operators. So as the momentum operator involves differentiations, the coordinate x treated as position operator and the momentum operator do not commute. That is, xp is not equal to px. So how can you see this? Because let xp, the left hand side, operate on a wave function, on an invisible wave function, let us say psi. So you get minus ih cross x d psi dx. And if you write px psi instead of xp psi, then you see you are differentiating, see, not only psi, but you are differentiating x psi. So the result is minus ih cross psi minus ih cross d psi dx. So xp psi is clearly not equal to px psi, and which means that xp is not equal to px. So the two results are clearly unequal. Thus, while handling operators, the order in which these are written is always important. And we also find from foregoing considerations that xp minus px is equal to ih cross. Okay? And xp minus px, that is defined as the commutator of the two operators x and p. So the commutators of the two operators x and p in this case is equal to ih cross, and it can also be verified that this is equal to minus the commutator of px. If you change the order of x and p within the commutator, then instead of xp minus px, it becomes px minus xp. So there is a minus sign. So xp, as I said, is called a commutator. According to Heisenberg's uncertainty principle, the two variables x and p are not simultaneously measurable. We have learned Heisenberg's uncertainty principle, and there we found that you cannot measure the position and momentum of the electron simultaneously. And here we find that these two variables, they do not commute. So there is an implicit connection between the simultaneous measurability of two variables and their commutation properties. Having defined commutation relation in operator algebra, let us work out two simple examples which will give you an insight of the things which we have been talking about. The first example, if the two operators have the same set of eigenfunctions, show that they commute. Well, this is a very important property of the operators. So how can you prove this? Well, I have given the solution. You can see the solution on the screen, but let me describe it. Let the two operators A and B have the same set of eigenfunctions psi n. Now, if the set of eigenvalues of these operators are an and bn, respectively, the eigenvalue equations are, as we all know, A psi n is equal to A n psi n and B psi n equal to small b n psi n. Now, what you do is that you multiply the first equation from the left by the operator B. So you get BA psi n on the left hand side. So when A operates on psi n, by the first equation you get A n psi n. So BA psi n will be equal to A n and then B operating on psi n. Now, from the second equation on the screen, well, B psi n is small b n psi n. So the result becomes A n B n. So this is the first result which you get, that B A operating on psi n is equal to A n B n. So similarly, if instead of operating B from the left, if you operate A from the left on the second equation, then you get AB psi n is equal to Bn A psi n equal to Bn A n. And since Bn A n are numbers, these are eigenvalues, so you can interchange A n and Bn. So Bn A n is equal to A n Bn. So the third and the fourth equation show you that BA operating on psi n is equal to AB operating on psi n, which means that AB minus BA operating on psi n is equal to 0, which means that the commutator of A and B is equal to 0. This means that the operators A and B commute. So I'm repeating this result because this is a very important result, that if the two operators have the same set of eigenfunctions, well, then you see these operators always commute. So this is a very important result which will be used later on. And then let's come to the second example. So in example 2, the operator O is defined as a differential operator, which is d squared dx squared. Well, this has a set of eigenfunctions psi n equal to e to the power 2nx, where n is a positive integer. So this is given. Now the question is, what are the corresponding eigenvalues? So let's come to the solution, which you can see on the screen. So when you operate O on psi n, it means that you are differentiating psi n twice with respect to x, and so this will give you 4n squared e to the power 2nx, and this is 4n squared times psi n, because psi n is equal to 2 e to the power 2nx. So you get O psi n is equal to 4n squared psi n. So comparing this with the general eigenvalue equation, which is O psi n equal to lambda n psi n, the set of eigenvalues is 4n squared. Since n is an integer, so if you put n equal to 1, you get 4. If you put n equal to 2, you get 16. If you put n equal to 3, you get 9 times 4 is 36, and so on. So we have come to the conclusions that, you see, the eigenvalues are given by lambda n equal to 4n squared, which means that the eigenvalues are 4, 16, 36, and so on. Let me mention one important thing in this connection. In general, operators with real or measurable eigenvalues are known as real or Hermitian operators. Well, this is just a definition. Well, if an operator has real eigenvalue, then the operator is called a real operator or a Hermitian operator. So for example, the Schrodinger equation H psi n E n psi n, well, this is Schrodinger equation expressed in the operator form. Well, in this equation, the Hamiltonian operator H is a Hermitian operator. Why is it so? Because its eigenvalues are the energy levels En, well, which are real and measurable. So this is an important definition. And then let us come to Schrodinger equation in 3 dimensions. So let us first talk about the time independent equation, because that's something more important for us. So what the way you have to generalize is that you have to replace d squared psi dx squared by del squared psi where del square is an operator which is d square dx square plus d square dy square plus d square dz square. So if you do that, then the Hamiltonian operator, you see, becomes h square by 2m, and then del square instead of dx square dx square, d square dx square plus v. So that is the form of the Hamiltonian operator, that is which you can see on the screen. So the equation can still be written as h psi equal to e psi. That is the second equation on the screen, h psi equal to e psi. So this form is still retained, well, even though you are writing the Schrodinger equation in 3 dimensions. Only you have to remember that the Hamiltonian is now 3 dimensions, which contains del square instead of ddx square. So in the same way, the time-dependent Schrodinger equation also has the same form, IH d psi dt equal to h psi, where h is now the Hamiltonian written in terms of del square. Okay. Now, we have to be a little cautious, you see, when we describe the motion of electron, let us say in an atom, let's say hydrogen atom. Because, you see, in a hydrogen atom, the Coulomb potential is a spherically symmetric potential. It is constant over the surface of a sphere. So it is convenient for us if we change right from the beginning, if we change the Schrodinger equation from Cartesian coordinates to spherical coordinates. So on the board you can see the coordinate systems, that is x, y and z, 3-dimensional coordinate system, well, on a plane, you see, which you can see on the screen. So here you see the coordinates of a point P is x, y, z in Cartesian coordinates, and in spherical coordinates it is r, theta and phi. So you know x, y, z, in these are the perpendicular. If you drop perpendicular, you see, from P to z axis, then you get the z coordinate, and if you drop a perpendicular from P to the xy plane, and then from that point you drop perpendiculars on x and y axis, you get the Cartesian coordinates x, y and z. And the spherical coordinates, sometimes it's called polar coordinates also. Well, in spherical coordinates, the point P is described in terms of a radius vector, well, in terms of r, which is its distance from the origin, and the angle theta which r makes with the z-axis, r theta. And then you have to be a little careful in defining phi in a right-handed system. Well, you drop a perpendicular from P, and you see, you join that point to the origin, and the angle which it makes with the x-axis, that is phi. I think the figure is self-explanatory, and you see, from geometry it's easy to see, find out the relation between x, y, z and r theta phi. The relations are x equal to r sine theta cos phi, y equal to r sine theta sine phi, and z is equal to r cosine theta. Okay, that's the relation between the spherical and the polar coordinates. So we have now to translate the Schrodinger equation in spherical coordinates. So you can see the Schrodinger equation, the time-independent Schrodinger equation. That's the first equation on the screen, and by now I think you're familiar with this equation. You have to remember it by heart. It's the most fundamental equation in quantum mechanics. So you see, this form is still retained in spherical coordinates. All that you have to do is you have to explain del square in spherical coordinates. So if you express del square in spherical coordinates, it becomes a bit cumbersome, and it takes a few pages, to come at this result. And you can see this as the second equation on the screen. That is the expression for del square as a function of r theta and phi. So it's a clumsy equation. It looks clumsy compared to what you find in Cartesian coordinates. the time-independent Schrodinger equation in spherical coordinates is easier to solve for electrons in an atom subjected to Coulomb potential, which is a spherically symmetric potential, as I've already mentioned, which is constant on the surface of a sphere with nucleus at center. Such potentials are also called central potentials. Students, we have now come to the end of this lecture, and before we end up, let me summarize what we have really learned from this lecture. Number one, the wave nature of tiny particles like electrons leads to time-dependent and time-independent Schrodinger equations. Time-dependent equation is useful for isolated atoms. For example, where an electron is subjected to Coulomb potential that does not change with time. And then number two, the Schrodinger equations are also expressed in operator forms, and the commutation relation for operators and its significance is described. And then finally, the time-independent Schrodinger equation in 3 dimensions is expressed in spherical coordinates for future use in the case of electrons in atoms, where an electron is subjected to spherically symmetric Coulomb potentials. So, in the next lectures, we will be applying Schrodinger equation to various systems to calculate the energy levels and the wave functions. So this is our aim for the next few lectures. Thank you.